Hello everyone. So I think in the previous video you would have been seen, right? D-logits was the uh, prime point of discussion as to why that's how it is calculated, and finally, after having good amount of discussion with the chat bot, chat GPT, I have some explanation for that. So the thing that's happening here, right, why it is this way and not the other way around, right? The major reason is that this logit maxes, right? It's a max function. It's a max function. It is not a continuous function. You can't differentiate that because obviously it's not a continuous function. You are just picking up a maximum out of the available options that you have. As a result, the theoretical differentiation that we were trying to do, right? That was where it went. Yeah, something like this. The theoretical differentiation that we were thinking, right? It won't apply to it because obviously, because yeah, it's not a normal differentiation as such. So in that case, PyTorch applies its own way of differentiation. So here is written PyTorch uses automatic differentiation to compute gradients, and the max operation is treated in a special way during the backpropagation. So in particular, the gradient of the max function is not computed in usual sense because max is not a differentiable everywhere. Instead, PyTorch computes the gradient with respect to the element of the input that were part of the maximum value. So what is happening is wherever we are plugging out those maximums in each of the rows, right? Those gets differentiated and we get a one in place of that. Apart from that, right, all others are zero. And it has a term that is known as subgradients rather than the gradients, right? It's a subgradient. As a result, you see this behavior. If you want, right, I will put this description in the comment section as well so that you can read. But this was something good to know that it's handled itself a bit differently so that we are able to backpropagate and move along. So that's why you see a different differentiation, way of differentiation for logits. Okay. Now we will move ahead. Um, okay. Sorry, where it was. What all we need to calculate here. Okay. So we had calculated till here. So this all we need to calculate now. Okay. So we are calculating with respect to h now. So h is here. H impacts logits. Okay, and then logits impact that. So we need to calculate dh. Okay, so it will be d loss by dh, that will be equal to d loss by d logits into d logits by dh. So this is the function that we are calculating. Okay, this anyway we already know, d logits. And what is the size of h? I don't know if any broadcasting or anything is that. It's a 32 cross 64 metric. Okay. And W2 and B2, what are those? Mm, okay, so there is a dot product happening with this, and there is an addition happening here. So logits is h at w2 plus b2. Sorry, w2. So when we differentiate with respect to h, anyway, this will be 0. Now what will be the dot differentiation of a dot product? So if you think a bit, let's take 2 by 3 and 3 by 4. So h11, h12, h21, h22, two rows, 3 columns, sorry. So h23, h13. So that is h. Okay, and b in that way, b in w in that way will be w. That has to be 3 cross 2, right? So w1 2, sorry, w11, w12, then w21, w22, w31, w32. So this will be multiplied by this will be multiplied by this will be multiplied, this will be multiplied by this. So if one of the element if I take as well, right? So it will be h11 into w11 plus h12 into w12 plus h13 into w13. Oh, sorry. Um, w21 h31. Now we are differentiating this with respect to h. Hmm. Mm, differentiating with H, right? So we'll get a 2 cross 2. What does differentiating with H looks like for that? I mean, H is like if H changes, how this gets impacted. So this is a dot product, not a normal multiplication, right? But if I see it in that way, break it completely. Um, I see multiple multiplications happening and then additions happening. So these are all means this multiply with this, multiply with this, multiply with this. So if I think in terms of graph, right, 3 multiplications happening and then addition happening. 3 multiplication having addition happening, 3 multiplication happening, and then all are represented in one way. Now if we have to say, and then B is added on top of each of them, and each of this element in itself is an element that is going forward, right? So if H increases, let's let's think it that way. And when I say H increases, all of those elements increase. So logits cross multiply. So for this, right, what I'm thinking is like this, it's happening. Yeah, something like this: x1, w1, x2, w2, x3, w3, all going here, and then an addition happening. So all this multiplication happening and then addition happening, something like this you can take, right? This is the dot product. Now if logits is here, right, and this is the B that is happening. So if this has a gradient, because it's an addition, the gradient will come here. Okay. So for this element, right, the gradient will simply be coming here. So when it's a so for all of this, right, I think it will just take the okay, but this will be with respect to this. If I have to talk about with respect to h, right, we need to move here till this is our h here. So what will happen? Addition is happening now. A multiplication. So again, addition is happening. So that gradient will come here. So the logits, whatever the gradient was here, right, it will reach till here. Now because it's a multiplication, so we will take data of this, multiply by this gradient and put it up here. So one of the element of that will be h11 into dlogit dot shape. Dlogit is not defined. Oh, sorry. Dlogit dot shape. But interestingly, that's a 32 cross 27, and h is 32 cross 64. So for each of those element, right? The gradient will be for h11 it will be w11 and d logits um so for this it will be logits um this has 27 values, that has 64 values. And means one thing I can realize, so w1 into some logits should be, so I think how it will go is, say logits is 32, so this dot product, right? Finally the dot product output that will come is 2 cross 2, 2 cross 3, 3 cross 2, 2 cross 2 will be the dot product. And the logits, this thing, right, will also be 2 cross 2 itself, for sure. That has to be 2 cross 2. So multiplication will happen and the output will be 2 cross 2. But the problem is the output, the logits that we are looking, right, as a very, sorry, the h, right, with respect to whom we are seeking, they have a pretty different shape. Okay, let's see. I don't see a way out here. Only thing that I can see is backprop is calculated for a um dot product. Hmm. Okay. So a dot b is equal to a1 plus b1. It is something like this. Suppose we have a loss as but depends on the reducing by we need to calculate the loss with respect to a and b. We need to calculate dl by d, dl by db. The gradient of the loss with respect to a, loss by a by this. Okay. This anyway is calculated. Oh, is it? That will be the size of b. I I usually get confused because these are arrays and this game. It's not just simply an okay. Hmm. Now then it's a pretty simple thing. So what he's saying is if so h at the rate w2 d of this d h will be equal to w2. Okay, and into this thing, and W2 is 64 cross 27 and this individual is 32 cross 27. 32 rows, 64 rows. Hmm. Not sure about that. Okay, at least I know this thing. So this won't be then um, L2 by W2, sorry, W2. This will give us h, and when we do with respect to p2, none of them matters. That will be 1. So d, sorry, I should write it like this, plus b2 plus b2, and the same will write b2 by b2 will, that will be 0, it will be 1. But this is fine, but how we will multiply 32 cross 27? Apart from broadcasting, I don't see anything. But let me calculate that and see how it goes. So th will be equal to w2 into d logits hmm I think I still don't think anything changes per se. Because w2 is of this size. D logits is that, let's see.
Of a operation, and both of these can be used. I just thought I would show an equivalent way to do it. And I'm using plus equals because we already calculated the logits here, and this is now the second branch. So let's calculate the correct answer. Next up, we want to continue with logits here. That is an outcome of a matrix multiplication and a bias offset in this linear layer. So I've printed out the shapes of all these intermediate tensors. We see that logits is of course 32 by 27, as we've just seen. Then the h here is 32 by 64. So these are 64-dimensional hidden states. And then this W matrix projects those 64-dimensional vectors into 27 dimensions. And then there's a 27-dimensional offset, which is a one-dimensional vector. Now we should note that this plus here actually broadcasts, because h multiplied by W2 will give us a 32 by 27. And so then this plus b2 is a 27-dimensional vector here. Now, in the rules of broadcasting, what's going to happen with this bias vector is that this one-dimensional vector of 27 will get aligned with a padded dimension of 1 on the left. And it will basically become a row vector, and then it will get replicated vertically 32 times to make it 32 by 27, and then there's an element-wise multiply. Now, the question is, how do we backpropagate from logits to the hidden states, the weight matrix W2, and the bias B2? And you might think that we need to go to some matrix calculus, and then we have to look up the derivative for matrix multiplication. But actually, you don't have to do any of that, and you can go back to first principles and derive this yourself on a piece of paper. And specifically what I like to do, and what I find works well for me, is you find a specific small example that you then fully write out. And then in the process of analyzing how that individual small example works, you will understand a broader pattern, and you'll be able to generalize and write out the full general formula for how these derivatives flow in an expression like this. So let's try that out. So pardon the low budget production here, but what I've done here is I'm writing it out on a piece of paper, Really what we are interested in is we have A multiply B plus C, and that creates a D. And we have the derivative of the loss with respect to D, and we'd like to know what the derivative of the loss is with respect to A, B, and C. Now, these here are little two-dimensional examples of a matrix multiplication. 2 by 2 times a 2 by 2 plus a 2, a vector of just two elements, C1 and C2, gives me a 2 by 2. Now, notice here that I have a bias vector here called C, and the bias vector is C1 and C2. But as I described over here, that bias vector will become a row vector in the broadcasting and will replicate vertically. So that's what's happening here as well. C1, C2 is replicated vertically, and we see how we have two rows of C1, C2 as a result. So now when I say write it out, I just mean like this. Basically break up this matrix multiplication into the actual thing that's going on under the hood. So as a result of matrix multiplication and how it works, D11 is the result of a dot product between the first row of A and the first column of B. And it's obvious this is just a bunch of multiplies, and adds. And so this is not scary anymore. It's not just matrix multiplication. It's just tedious, unfortunately, but this is completely tractable. We have DL by D for all of these, and we want DL by all these little other variables. So how do we achieve that, and how do we actually get the gradients? Okay, so the low budget production continues here. So let's, for example, derive the derivative of the loss with respect to A11. We see here that A11 occurs twice in our simple expression, right here and right here, and influences D11 and D12. So what is DL by D A11? Well, it's DL by D11 times the local derivative of D11, which in this case is just B11, because that's what's multiplying A11 here. So, and likewise here, the local derivative of D12 with respect to A11 is just B12. And so B12 will, in the chain rule, therefore, multiply DL by D12. And then because A11 is used both to produce D11 and D12, we need to add up the contributions of both of those sort of chains that are running in parallel. And that's why we get a plus, just adding up those two contributions. And that gives us DL by D A11. We can do the exact same analysis for the other one, for all the other elements of A. And when you simply write it out, it's just super simple taking of gradients on, expressions like this. You find that
That looks like a dot product to me. Right by this. So here dot product this multiplied by this multiplied by this multiplied by this multiplied by this. These are all the values. Oh, nice, huh?
this matrix DL by DA that we're after, right? If we just arrange all of them in the same shape as A takes, so A is just a 2 by 2 matrix, so DL by DA here will be also just the same shape tensor with the derivatives now, so DL by DA11, etc. And we see that actually we can express what we've written out here as a matrix multiply. And so it just so happens that that all of these formulas that we've derived here by taking gradients can actually be expressed as a matrix multiplication. And in particular, we see that it is the matrix multiplication of these two matrices, matrix multiplying B, but B transpose actually. So you see that B21 and B12 have changed place, whereas before we had, of course, B11, B12, B21, B22. So you see that this other matrix B is transposed. And so basically what we have, long story short, just by doing very simple reasoning here, by breaking up the expression in the case of a very simple example, is that DL by DA is, which is this, is simply equal to DL by DD matrix multiplied with B transpose. So that is what we have so far. Now we also want the derivative with respect to B and C.
So with respect to B, it will be DL by dd matrix multiplication A transpose and with respect to C, this will become 0, this will be 1. Another one. Multiplication with a unit vector. These all will become 1, 1, 1, 1, 1, 1. Okay, because when we differentiate with C1, this will 0, this will be 0, this will be 1. So here we'll see 1 coming. Here we'll see again 1 coming from here. That way all will be 1. So this vector at the rate, this is a unit identity vector 1, 1, 1, 1 will be there.
Now, for B, I'm not actually doing the full derivation because honestly, it's not deep. It's just annoying. It's exhausting. You can actually do this analysis yourself. You'll also find that if you take these expressions and you differentiate with respect to B instead of A, you will find that dl by dB is also a matrix multiplication. In this case, you have to take the matrix A and transpose it, and matrix multiply that with dl by dd. And that's what gives you dl by dB. And then here for the offsets, C1 and C2, if you again just differentiate with respect to C1, you will find an expression like this, and C2, an expression like this. And basically you'll find that dl by dc is simply, because they're just offsetting these expressions, you just have to take the dl by dd matrix of the derivatives of d, and you just have to sum across the columns.
Oh, yeah, this is 1, 1, 2, 1. Column 1, 1, 2, 2, 2, column 2. You have to just sum it across them. Nice.
And that gives you the derivatives for C. So, long story short, the backward pass of a matrix multiply is a matrix multiply. And instead of, just like we had d equals a times b plus c, in the scalar case, we sort of like arrive at something very, very similar, but now with a matrix multiplication instead of a scalar multiplication. So the derivative of d with respect to a is dl by dd matrix multiply b transpose, and here it's a transpose multiply dl by dd. But in both cases, it's a matrix multiplication with the derivative and the other term in the multiplication. And for C, it is a sum. Now, I'll tell you a secret. I can never remember the formulas that we just derived for backpropagating through matrix multiplication, and I can backpropagate through these expressions just fine. And the reason this works is because the dimensions have to work out. So let me give you an example. Say I want to create dh. Then what should dh be? Number one, I have to know that the shape of dh must be the same as the shape of h. And the shape of h is 32 by 64. And then the other piece of information I know is that dh must be some kind of a matrix multiplication of d logits with w2. And d logits is 32 by 27, and w2 is 64 by 27. There is only a single way to make the shape work out in this case, and it is indeed the correct result. In particular here, h needs to be 32 by 64. The only way to achieve that is to take d logits and matrix multiply it with, you see how I have to take w2, but I have to transpose it to make the dimensions work out. So w2 transpose. And it's the only way to make these, to matrix multiply those two pieces to make the shapes work out. And that turns out to be the correct formula. So if we come here, we want dh, which is dA, and we see that dA is dl by dd matrix multiply b transpose. So that's d logits multiply, and b is W2. So W2 transpose, which is exactly what we have here. So there's no need to remember these formulas. Similarly, now if I want dW2, well, I know that it must be a matrix multiplication of d.
So it has to be W2 is 64 by 27. So 64 has to come in front. Only way possible is to transpose H. So H dot T. That makes it so H will be H transpose will be 64 cross 32, and D logits is anyway 32 cross 27. So we will get a matrix of 64 cross 27. This one happened, and C, what was the third term here? Sorry, db2 d b2 will be equal to logits dot sum, like this it has to go, right? That is by default, I think. Keep them equal to होना बरस का मैंने संभाला. This happened. Yo.
Logits, and I don't know which way it is, so I have to come to that has to 27 to work. That's logits. Is same way axis 27. Eliminate this dimension. So it's this. So this is so that's kind of like the hacky way. Let me copy paste and delete that, and let me swing over here, and this is these three, and we're checking that we see that H, W2, and B2 are.
This is working fine, right? Yeah, this is true. Okay, I think some miscalculations happened, but it was good. Okay, now shit, I missed it, but anyway, it's fine.
And
Okay, that was it.
Run, and we see that
Mm. Next is HP React. So so it is D loss D loss by D HP React is something we need to calculate. HP React impacts H. That's it. HP Reacts impact H. So dl by dh into dh by d HP React. Now dh by dhp React will be equal to d of tan h HP React by dhp React. Differentiation of tan h differentiation of tan h. So 1 minus tan square h. Okay, okay. We're not interested in the explanation anyway, but um, so h is tan h, right? H is tan h, yeah. I mean, h is tan h, so 1 minus h square. Let me just check the shapes. H dot shape HP React, and they will be same. So it's an easier one. Um, so I believe DH will be equal, sorry, DHP React will be equal to what we see here, right? DL by DH, that is DH into 1 minus 10, 1 minus square minus H square walked. Next is BN gain. BN gain is only one place we see BN gain impacts this individual. So d loss with respect to HP react, and then d HP react by dBn gain. Yeah, right. So that should also be pretty straightforward. So that will be dl by d um bn gain dl by d hp react into d hp react by bn gain. First part is anyway is this what we have calculated? That will be DHP react by this will be 1. No, yeah. So that will be BN raw. Okay. Let me check the shape of these individuals. Dot shape D. No worries then. It's anyway a multiplication, right? So um um sola perseca D D BN gain we are calculating. So dBn gain will be d bn raw into this thing, and next let me show this because this will be equal to bn gain into dhp react, and with bias if I have to do right, if this become bias, um this will anyway be 0, so it will be 1 because it's an addition, so the same will percolate there. So t bias raw batch norm bias. Mm, it should work. I'm not sure what's the issue.
H linear layer for the H. So we want to derive done this way, but luckily Google image search does not let us down, and it gives us the simpler formula. And in particular, if you have that A is equal to tan H of A squared, the tan is here. We have the math to figure out the derivative square. Is going to be our can. Okay, next the BM bias. So the element thing happening in this line of code though. So you see how BN gain and BN bias are 1 by 64, but H preact and BN raw are 32 by 64.
Yo. Good learning. That's where the issue is coming. So dbn raw. So dbn raw, dbn gain are very different. Okay, so dbias is anyway fine. So when we do that bn raw 32 cross 64 multiplied by HP react, it should work, but bn gain should be a 1 cross 64 play. It's like this. So if you have to do a 1 cross 64, right, you need to add in this shape or form. So it can be oh sorry. Sorry, it should be 0, right? 0 means like this, it happens, okay. Uh, yeah, 0 dimension is this one. 1 is like this if you want. So it should be 0 here. Now what? Now the other one, right? bn raw we want to calculate, and there will be multiplication between these two. One is 32 cross 64, the other is 1 cross 64. So 32 cross 64, 1 cross 64, it will get deduct upon, and the multiplication will happen, and we should get an output of 32 cross 64. Okay, right, I think it should have worked. um, so it should have worked. Hmm. Oh, bias is false, is it? Okay, 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 okay. Oh, oh, okay. How come bias is a false? HP React is 32. Ah, okay, but bias is 1 cross 64, right? So, you need to again do the sum so that you get 1 cross 64. Okay, okay, got it. So the same thing applies here as well. All true. I will, yeah, very soon. Sorry for that. So we'll resume. One big learning from here is first check the shapes. And then obviously if it's a special case of dot product or maximum or something, it will be different, else it goes as usual. Now we are going to calculate with this. Again, it's a multiplication play, right? And if is also not used anywhere, I believe. No, it's used. So I see B and if used being two places. So its gradient will be a bit different. So let's calculate for this inverse. So that will be simple, right? So if we are like, okay, first let's check the shapes of everything here. That's the learning. Okay. So we are calculating with respect to this, okay? So when we are differentiating, right, because it's a multiplication, so it will be B and F, sorry, B and F into dB and raw. Okay, but the problem is B and F is 32 cross 64, and let's get the dB and raw also. That is 32 cross 64. So when these two get multiplied, right, we get an output of 32 cross 64, but we are calculating for this, right? There's only one cross 64, so we again need to do all the additions. Let's now calculate this individual. BN var. So BN var has two places. No, only one place. Here is the one. Okay. So Bn var impact inverse and then inverse impacts its own way. It's 1 by, so a plus c to the power 0.5, right? So that is a plus some k constant 0.5 minus 0.5 is the power, and we are differentiating with respect to Bn var, that is k, minus 0.5 by dk. No, let's not keep it, let's keep it p, and let's keep it c as a constant. Okay, so we are differentiating this. So what will happen? The power comes out, the power comes out. Let me do it here. I'll put it different. Into power gets multiplied by, it's added minus 1 as well. It's actually minus 1.5, minus 0.5, minus 1, minus 1.5. From half, it became 3 by 2. Means that's the cube, right? So this was, say, was m equal to this. So minus 0.5 into m cube. That's for sure, right? Yeah. Now let's just check the shape of these individuals. All are same, so no issues. By mistake, I changed the value of the variable itself. Approximate is true.
So we have to be careful with that and make sure that all the shapes work out fine and that the broadcasting is correctly backpropagated. So in particular, let's start with, otherwise I would just get 64. Now, I don't actually buy B2, why, as long as your work to be multiplication. To check that we are getting back in is the output of the standardization. So here what I'm doing, of course, is I'm breaking up the batch norm into manageable pieces so we can backpropagate through each line individually. But basically what's happening is bn mean I is the sum. So this is the bn mean I. I apologize for the variable naming. Bn diff is x minus mu. Bn diff 2 is x minus mu squared, here inside the variance. Bn var is the variance, so sigma squared. This is Bn var. And it's basically the sum of squares. So this is the x minus mu squared, and then the sum. Now you'll notice one departure here. Here it is normalized as 1 over m, which is the number of examples. Here I'm normalizing as 1 over n minus 1 instead of n, and this is deliberate, and I'll come back to that in a bit when we are at this line. It is something called the Bessel's correction, but this is how I want it in our case. Bn var inv then becomes basically Bn var plus epsilon. Epsilon is 1 negative 5, and then it's 1 over square root is the same as raising to the power of negative 0.5, right? Because 0.5 is square root, and then negative makes it 1 over square root. So Bn var inv is a 1 over this denominator here. And then we can see that Bn raw, which is the x hat here, is equal to the Bn diff, the numerator, multiplied by the Bn var inv. And this line here that creates H preact was the last piece we've already backpropagated through it. So now what we want to do is we are here and we have Bn raw, and we have to first backpropagate into Bn diff and Bn var inv. So now we're here and we have d Bn raw, and we need to backpropagate through this line. Now I've written out the shapes here, and indeed Bn var inv is a shape 1 by 64, so there is a broadcasting happening here that we have to be careful with. But it is just an element-wise simple multiplication. By now we should be pretty comfortable with that. To get d Bn diff, we know that this is just Bn var inv multiplied with d Bn raw. And conversely, to get d Bn var inv, we need to take Bn diff and multiply that by d Bn raw. So this is the candidate, but of course we need to make sure that broadcasting is obeyed. So in particular, Bn var inv multiplying with dBn raw will be okay and give us 32 by 64 as we expect. But dBn var inv would be taking a 32 by 64, multiplying it by, needs me to make, let's erase this. Let's comment out the, we'll actually notice that db and diff, by the way, is going to be incorrect.
Because
so when I run this,
used it 2 places.
bn var inv is correct. Bn diff is not correct. And this is actually expected because we're not done with bn diff.
diff is used here.
So in particular, when we slide here, we see here that bn raw is a function of bn diff, but actually bn var inv is a function of bn var, which is a function of bn diff do, which is a function of bn diff. So it comes here. So bdn diff, these variable names are crazy, I'm sorry. It branches out into 2 branches, and we've only done 1 branch of it. We have to continue our backpropagation and eventually come back to bn diff, and then we'll be able to do a plus equals and get the actual current gradient. For now, it is good to verify that CMP also works. It doesn't just lie to us and tell us that everything is always correct. It can in fact detect when your gradient is not correct. So that's good to see as well. Okay, so now we have the derivative here, and we're trying to backpropagate through this line. And because we're raising to a power of negative 0.5, I brought up the power rule, and we see that basic 0.5, and now raised, we would have to also apply a small chain rule here in our head because we need to take further derivative of b and var with respect to this expression here inside the bracket. But because this is an element-wise operation and everything is fairly simple, that's just 1. And so there's nothing to do there. So this is the local derivative, and then times the global derivative to create the chain rule. This is just times the b and var. So this is our candidate. Let me bring this down and uncomment the check. And we see that we have the correct result. Now, before we back
PN for, right? Okay. I'm getting exact, but very similar. I think it should be okay.
and we see that we have the correct result. Now, before we backpropagate through the next line, I wanted to briefly talk about the note here, where I'm using the Bessel's correction, dividing by n-1, instead of dividing by n.
That we'll see next.